Alright, today we're going to be designing a bicycle frame using topology optimization in Ansys. So the first thing we're going to do, this is just what happens if you open the workbench. So you just go to Start menu, all the way down to the bottom, it's the last one, it's called Workbench 2020 R1. Go ahead and click on that and this will load up. First thing we're going to do on the left here, under Analysis Systems, you will notice a thing called Topology Optimization. Now I did say that that's what we're going to be doing, but don't click on that just yet because we got to go to Static Structural first. So the first thing we do, we click and drag it in. You can either double click on it or you can click and drag it in. Later we'll see why dragging is a better option, but for now, you see this highlighted. I can rename it Bike Frame. And engineering data is already checked. So let's go ahead and double click on that and take a look. And this is just choosing your material. Literally, it's just steel. Down here we have the material properties. This will also become useful later. But for now, I'm going to leave it for steel. Go ahead and close it. And alright, so as we are going through the problem, Ansys, you will find, is very helpful. Things will turn into green check marks if they're correct and good. Not only in this menu, but in all the internal menus as well. So, see, we have green check mark. That's good. That means it's done. We don't really have to pay attention to that one now. We go to geometry and double click on it. And you can see it's not really doing anything, but be patient because it says down here, ooh, excellent, just in time. It's starting space claim down here. That means it's doing something. Alright, so here we are on space claim, and what I'm going to do is I'm first going to draw a line that's about 300-ish centimeters long. It doesn't really matter what angle, but I'm going to do it like that. And bottom bracket probably goes here, and it's really slack, so it's going to be like this. It's going to be huge. Alright, perfect. Now, I hope you see a bicycle frame here. Because most bicycle frames, right, they're going to look like this, and then they have the rear wheel goes like, oh, that's pretty big. You know, something like this. Front wheel's like over here. Handlebars connect up here, and the crank is like here. The seat goes here. Right? The frame looks something like this. Big triangle in the back, triangle in the front, right? Triangle in the back, triangle in the front. Except this main seat tube here. What we're going to do is see if Ansys can come up with a better idea for bicycle frame. So we're going to start with this outer mold line, like so, and extrude it into a big, thick sheet of metal. And we're going to apply the loads to it as appropriate and have Ansys run topology optimization and see if it'll come up with either this shape. If that's the case, this is the most optimal design, or some other kind of shape. So what I'm going to do is undo all these circles, and this is the shape of our frame that we're going to start with, okay? But first, before I extrude it, I'm going to put some circles, just that oh, it's a bit small actually. Okay, no real reason why they're any particular size. I think that's the same size. But basically this is going to allow me to put loads where I want them. This is a bit close to the edge. Again, it doesn't really, I'm sort of arbitrarily placing these. They're not really, you know, planned out really well, but this is the seat. This is where the cyclist's pedals are going to go. This is where the rear wheel is going to go. This is a bit close to the edge. I hope that's okay. And this is where the handlebars go. Okay, and then Ansys, then we'll apply the loads down here, down, fixed constraint here, and then forwards and down here. And then we'll put the front wheel in here and run it. And then Ansys will eat away at this frame material here, which it decides is not useful. And then we'll have a new bicycle frame. Okay, so now we have 4 circles in this rhomboid shape, and I'm going to go to pull it upwards. And picking the thickness is kind of like an eyeballing kind of a game. It's just, you know, if I make it thicker, I'm just going to have to put more load on it to get the same result, right? So I'm just sort of eyeballing it to see what a mountain bike frame width kind of looks like versus its size. So it's like aspect ratio in a way, I suppose. Looks good to me. The thickness to the size. And okay, next up we're going to pan up to the front, and you'll see why I'm doing this in a second. But I'm just gonna sketch on this front face, and I'm gonna put like a rectangular area and just extrude it a tiny little bit. 0.75 is good enough. Okay, and that's gonna be where the front handlebars connect, because this hole is where the load is applied, and I need to simulate where the front wheels are. Otherwise, it's only fixed in one place where this rear wheel is, and it's gonna put a lot of moment on it. So I need somewhere for the front wheels, because on an actual bicycle, that's where the steerer tube goes in the bearing, so that the force from the weight of the rider and the handlebars is going to go down into the front wheel through the fork. In our case, we don't have a fork. We're not going to simulate the suspension or the wheel, so I'm just going to say that's a fixed constraint on that face, and because I only want it to optimize this part of the frame. Okay, so that's it. We are done with space claim. We can go ahead and close out of that. And as you can see, it's now green check mark. Perfect. So model is the next one. Double click. And again, it's starting mechanical. So this is the simulation part of the software, where it's going to automatically import the geometry we just made. All right. So here's our part. At first glance, it looks like it's upside down or something, but good thing I put this part in, because now I can tell this is supposed to be the front. And I'm just going to pan it around like so. And this should be the same orientation that we had earlier. Now you'll notice one thing over here, that in geometry, there's 4 surfaces plus a solid. Now what that means is I did it wrong. So back into geometry with space claim. As a matter of fact, I don't think I should have closed out of it. I should have just left it running. You see there's 2 things here, right? The surface, which is what we drew, the sketch, and then the solid, which is the actual piece of material that we extruded upwards. So we're going to go to surface and right click on it and suppress for physics. Good. Now we go back to model and we say update, because we just changed something in geometry, right? I don't think it automatically will update the model. So now, perfect, green check mark. And we go back into here, and perfect. You see this, the solid, the surfaces are gone. It's just left with the solid. That's perfect. Actually, when I right clicked on it and said update, it meshed it for me. I wanted to show you that step, but what you would do, this wouldn't be checked off. You would right click on it and say generate mesh, and then something like this would show up. You see very coarse kind of a mesh, and instead I'm going to go to sizing. Use adaptive sizing. I'm going to say yes, I would like adaptive sizing. Go to resolution. This goes up to 7. I'm going to leave it at about 6. And then, well, just for demonstration purposes, let me hit solve. There you go. Now we have a finer mesh. But the thing is, I know from experience, and you can probably figure out, that the parts where there's lots of load, like in the corners, or load concentrations, like sharp edges like this, what I'm really interested in here is the fact that loads are going to be distributed throughout this piece of material through these circles. And because there's going to be things happening, I would argue that there's more things happening in this very specific location at each circle than there is like here, for example, right? So this is the part where Ansys is going to remove material. I'm just guessing based off this, because there isn't that much load, right? But in these localized areas where the load is concentrated, a lot of stuff's going to be happening, so I'd like to have more resolution. Remember what we learned in class, that higher resolution gives you better results, typically, right? Obviously, with doing that by hand, it's just prohibitively expensive as far as time and effort is concerned, but we have a computer, so let's just turn it all the way up. So we're going to go to span angle center, say fine, and update. And then what that's going to do is all the localized, where sharp things are happening, there you go. I'm going to hold Control and do the middle mouse button to pan around like this. See, lots of elements right where the there are features, for example. And all right, looks good. The next thing, we already meshed it, but we do not have a solution. So we're going to click over here, static structural, right click, insert a bearing load. I'm just going to zoom in and try to click, but there we go. Try to get this whole cylinder, right? If you're having trouble picking it, like so, it's because you're zoomed out too far. Zoom way in, click inside, and you're good to go. Now, I have the X, Y, and Z components here, right? And I notice X is this way, Z is downwards, and Y is outwards. So I'm mainly going to be concerned with X and Z, like I said. The question is, how many newtons do I actually put on it? So let's do a little bit of math. I've managed to actually do some of it by hand on a piece of paper, and I scanned it in so we can take a look at it. But let me walk you through the load cases first. So first of all, on a bicycle, right, the seat, I'm thinking most of the time the rider's going to be sitting on it. It's plausible that he is about 100% of his weight on the seat. I mean, like he sits on the seat and takes his feet off the pedals and doesn't touch the handlebars, then 100% of the weight is on the seat, right? But it's all downwards. And I'm taking an average rider. I'm going to say a male rider, 160 pounds. That would be 73 kilograms, right? So I'm going to take 73 kilograms and convert that into newtons. 716 newtons. Enter. But the thing is, I've picked this, but I haven't applied it yet. I haven't applied this bearing load to this surface, so I need to go in here, geometry, say apply. So now we've got a little arrow. We know we're good to go. And then let me think. On the handlebars, right? He's going to be, I would say, probably half. Well, first of all, let's go over what the load case is. The load case, what I'm going to be looking at is this. It's called a huck to flat, which means you jump it off a jump or something, right? But you land on something that's flat ground. Normally, you'll notice people land big jumps on what looks like another jump, right? So they come off, taking off here, and they land on something that's like sloped downwards, so that the impact isn't too big. But in this case, this is flat ground. So, courtesy of Pink Bike, by the way. And over a short period of time, right, the load goes through the forks and gets absorbed by the suspension. At this point, the suspension isn't doing anything anymore, and all of the load of accelerating the rider upwards, or should I say decelerating him from falling downwards, is now going through the frame, right, for a short period of time. I would argue that the handlebars aren't really seeing that much force, but it's mostly in the pedals. But I'm going to put, let's say, half of his weight on the handlebars here. Okay, and it's going to be somewhat forward and somewhat downward. So we're going to go to bike frame and pick the surface. Right-click, insert, bearing load. Now I want components. And I said half forward, half down, right? Half of we said his weight is 716. 716 divided by 2 is 358. So we're going to go 358x and in the Z. And notice I'm putting positive numbers because of the direction of the arrow. Okay, and that looks good to me. So it's that kind of a direction. Notice that the front wheel, we've got to put a fixed constraint, right? So I'm going to go to insert and go to fixed support. Right here. And down to the bottom bracket. Now this is very interesting because according to what I saw here, right, it looks like most of the weight is being accelerated is transferred through the bottom bracket, meaning the pedals. He pushes down with his calves into the pedals, which goes through the bottom of the frame right here. Let's go through the math really quick. So this was the load case, 10-foot huck to flat, okay? I highly recommend you follow my cursor because I wrote this kind of backwards, right to left. So I'm gonna walk you through it though. The load case is 10-foot huck to flat. 10 feet is equivalent to 3 meters, right? Let's work in SI units just for convenience. This is an equation from kinematics, right? Final velocity squared equals initial velocity squared plus 2 times the acceleration times the distance over which you're accelerating. Okay, so we know that the final velocity, we don't know that. This is while he is still falling, right? So we need to calculate how fast he's going when he hits the ground from 10 feet in the air. So final velocity is what we're looking for. Initial is none. Let's assume he's got no downward velocity when he comes off that jump at 10 feet. So 0. 2 times acceleration due to gravity, and then distance is 3 meters, which is what we said. So we evaluate for final velocity, and we get 7.67 meters per second. When we go over to this step here, we're going to use another equation from kinematics, except this time the initial velocity, this is when he's colliding with the ground. Okay, so this is when he's falling. We needed to find how fast he's going when he hits the ground. Now we plug that into here to find how much acceleration is input onto the frame, and from which we can find the force on the frame. But we have acceleration over a time period, which I estimated to be at 100 milliseconds, which is 0.1 of a second. I input the initial velocity here. We know final velocity is 0 because he's not going down anymore. So 7.67 to 0 over 100 milliseconds gives us an acceleration of 76.7 meters per second squared. I plug that into F equals ma, using m being the rider's mass, and we get the force of 5,600 newtons. That's going to be the force that we apply downwards on this right here. Right click, insert bearing load. Don't want vector, we want a component, z, 5,600 newtons. Very good. And I would say that if he's going downhill and braking and applying a lot of force on his feet, there would be an x component as well. So I'm just going to, for good measure, put like 1,000 in case he's braking really hard or something. Okay. Actually, this vector looks like it doesn't change at all. I'm going to put 2,000. There we go. So what I did the math for is this number here. So we actually have a finite number of newtons that we need to meet with this frame. Okay, the handlebars, it was more or less an estimate. The handlebars were more or less an estimate based on his body weight. This is just his body weight. And then his feet, that was an actual calculation. You see this fixed support here that doesn't have a check mark? That's probably because I forgot to apply it. So let's double click on that guy and geometry. This face right here, say apply. There we go, now we got green check mark. Perfect. And bearing load, this should be the bottom bracket, right? Perfect. And what's left is the back wheel. We need to put a fixed support in here. Now the thing is, I don't really want to, I don't want a fixed support because that would, what's going to happen, right? This frame is going to bend in the middle because all the load's in the middle, but it's supported at both the front and the back. It's just going to go down in the middle, right? Which would impart a twisting kind of a moment on this back wheel if it was fixed. But in reality, I don't think there's going to be a fixed constraint, right? Instead, there's going to be a wheel on a bearing. So instead, I'm just going to put I'm going to put in a cylindrical support. We got tangentially free, but axially and radially it's fixed, which means it cannot move axially, as in slide along the y-axis, and it cannot move radially, as in translate, outside of this shaft, really. But tangentially, it's free to rotate. So I'm going to go ahead and right-click on solution and say solve. check down here, and it's good to go. And that's exactly as expected. And the solution's done. Okay. You can go to solution information. It's just got a lot of behind the scenes sort of information. This is good for debugging if you really know what you're doing, but for our intents, let's go to solution. Under the solution tab, we're going to go to stress and go to equivalent von Mises. Now you'll see it just appeared here, but it didn't actually change anything. So we have to, it's got the little lightning symbol. We have to right click, evaluate all results, and perfect. You see no moment was restrained by this axle. It's just sort of held in place like an axle would, but it didn't prevent it from rotating. Perfect. Front wheel did, which is also what we wanted. A lot of load down here. All right, looks about like what I expected. Good. All right, let's go back to here, and you'll see all green check marks. That's perfect. Okay, and what we're going to do now, we can take topology optimization, take it and drag it in. Don't put it here. Don't put it here. Don't put it there. We're going to drag it onto the solution. And what that does is makes a little pipeline. It takes the solution from what we did previously and puts it into this topology optimizer. Okay, and you'll see here, we got these are all green, so that's good. The model, if you check it, it's just going to look like what we made previously. So let's double click on setup. And you will see here, all this green, all the stuff we did earlier, right, is still here, except now we've added on this topology optimization. Analysis settings, this should be, you know, good to go pretty much by itself. You'll notice that design a region that it's allowed to touch is this, wow, this is blue part, but see it's kind of red in the corners? That's because it's excluded, and it already knows that it's not supposed to touch places where forces are applied or fixed constraints are. Okay? See, like so. Those are the excluded regions, and the objective, we're just going to leave this alone. This basically tells it what to optimize. You've all done optimization problems in calculus before, right? It tells you which value you want to optimize while minimizing something else. The constraint we've got here is 50%. We can change this afterwards depending on the result that we get and the resulting factor of safety, but I'm just going to leave it at 50 now. All right, so I don't think I was particularly clear at that part. 50% represents the amount of mass that the program is trying to retain. It's just like I said earlier, if you're going to do a calculus optimization problem, the value that we're trying to optimize here is the strength of the frame, or rather the stiffness of it based on our load case, while we are trying to minimize the mass. Right? Obviously, we want the strongest frame possible while keeping the lowest weight. So that's what the 50% represents. So basically, the main takeaway here is the percent of mass to retain slider is your adjustment for changing the result of the mass optimizer. Solution, go ahead and, well, instead of right clicking and saying solve, I'm just going to click on this solve here just for the sake of it. And looks like we're done here. Let's go and see what the computer came up with. So let's go to topology density. So this is our optimized bike frame. Does that actually surprises me a lot, because look at that. It's the same. All right. So now that we're done with this, what does that tell me? They've had the bicycle frame design correct for the past 50 years, 70 years, probably even more than that. All right. Perfect. As you look at the shape of this optimized region, right? It's sort of taken bites out of parts where there's not very much load. This isn't particularly manufacturable. You see how in this, right? It's pretty simple. You just take a pipe, another pipe, another pipe, some slightly different pipes which are flattened in certain areas, a smaller diameter pipe, and a little piece of metal, and you just weld it, you know, at all the joints. And it's very well, not very easy, but relatively manufacturable. If I gave you a sheet of metal and I told you to make this shape, it'd be very difficult. So unless we 3D print it, which was very hard to do with metal, it does exist, but it's expensive, this is hard to make. So what we got to do now, this doesn't really help us in design other than tell us that, you know, it should be this kind of a shape where this part connected, you know, and we could cut out holes here. This doesn't really help us with the design. So what we have to do now is go to Topology Density, which is where we were, right click, export STL file. So that'll export this, what we have behind, into an STL file, which we can then use. So I'm gonna go, and I've already done it as you can see, but I'm gonna call this optimized 2, and I say save, and we go back to here, and we're literally going to start over by going to static structural, drag it in somewhere else. We don't have to put it on solution or anything, just a new standalone system. I'm going to check engineering data, make sure it's still in steel mode. Yes, it is. Geometry, double click. And this is where the optimized file was saved. I'm gonna take the one we just made and literally drag it in. Look how easy that was. Zoom out. And I kind of want to look top down. I'm going to go to top view, and there we go. So that's what we were looking at before in here, except now it's a step file. And what I'll do is go ahead and start sketching. Take the sketching tool, start at this point, like so. And I'm actually going to overshoot these corners a little bit. You notice it snaps too. This is why we imported a file, right? I'm gonna overshoot. I'm gonna press. You see, it's like hinged off of that. I'll press escape and repeat. Again, overshoot it, but snapping too. I can ignore this little extra piece here now, and I'm not sure this top line is gonna work actually. But so what I've done is I can either click here or press T for trim, and just trim off the excess pieces. Like so, 1, 2. Perfect. And now we gotta put the circles in. So I'm gonna go circle tool. I'm literally redesigning everything just the same as it was before. And over here, except I'm using the previous model as a template, right? And the reason we imported the previous one was now we could use it, you know, literally the snap to feature is so useful. So I'm gonna make some triangles that are sort of vaguely the shape of what Ansys has suggested, like so. And another one here. Perfect. And it's generally a good idea to radius your corners. So I'm gonna go to pull and literally just pull the corners in. Make sure you don't run over these circles, but oh, you gotta press escape to stop editing that one. Just radius your corners like so. This hole is a little bit close to the edge, but since most of the load path is upwards and not down, that's okay. These corners are also quite, so I say, sharp. But it doesn't appear that I can use the pull tool on this corner here. Yeah, it doesn't seem to work. So what I'm gonna do is go ahead and pull on this whole face, right? This is what we just designed. But I don't know how much to pull it up by, so I'm gonna turn the original, remember this optimized file that we imported? I'm gonna turn it on. I'm going to pull it until I can see the original file like so. And that's it. Okay. And now that we actually have this frame shape, we go to pull and, oops, press escape, right? And pull the corners in so we can radius them. Perfect. So if you can't radius the corners in the sketch mode, just go ahead and extrude it upwards like I did. Just use the pull tool, give it some thickness, and then you can still pull on the edge after the fact like I'm doing right now. And it should work. Okay, so we got nice radius corners everywhere, and I'm thinking this is gonna be a super strong frame. So let's take this guy and go back here, go and mesh it up and run the FEA again. So we're literally starting over with the new design and seeing if it actually passes stress or not. Make sure at this step that you go ahead and, we only used optimized as a crutch, right? So I can go ahead and click on it and press delete. Perfect. Go in here, model, and update. Okay, so here is this, and again, I forgot to turn off the surfaces, so we just got to, I can close this, huh? And same with this guy. Just to reduce confusion, go to surface, right click, suppress for physics, and go back to here and update it. There you go. You got a nice thing here, and right click on mesh and generate a mesh. I hit update. I have to press generate mesh. Now it's meshed it. I'm going to go to sizing, adaptive sizing. Yes, I would like adaptive sizing. Resolution, good. Span angle center, fine. Generate mesh. Now it's much finer, especially around the corners. I just realized I forgot to put in the fixed where the front wheel is going to connect. So I'm going to sketch on this front face and just put in a little rectangular area here and go to pull that out by the smallest amount. Okay, all I need is something where I can select the face instead of the whole thing. Right, so I'm going to go back and update it yet again. Oops. Update. We go back into here. Perfect, we got this. We do have to mesh it again though. Generate mesh. Looking good. At this point we can go ahead and, wow, that's a pretty fine mesh. Look at that. Look at all these corners. I'm gonna select this, insert. Oh, I didn't click on static structural. Click here, right click, insert, bearing load. Now I'm just gonna put in, just so that we're comparing apples and apples, I'm gonna put in exactly the same numbers as we did before. So 716 newtons downwards for the rider, because that's his weight. For the front here, right click, insert a bearing load, components, the X, exactly the same as before. I've got it written down here, 358 newtons in the X direction and 358 in the Z direction. Perfect. And a fixed constraint on this guy here. Insert a fixed support. Did I say apply? Yes, I did. Good. See all green check marks. It's perfect. Whoops. And select this face. I'm going to insert again a bearing load. Change the vector to components. X direction, I've got 2,000 newtons, and Z component 5,600 newtons. I applied the face, good. And then last but not least is the not quite fixed but still a constraint. Insert a cylindrical support, except I want fixed tangential to be free. Again, allows it to rotate, okay? And solution, solve. Oh, we got some. Create automatic connection. Huh, look at that. Isn't Ansys great? It's done. Okay, so we click on solution, go over to the solution tab. Go to stress, equivalent von Mises. Again, we have to say, evaluate all results. And let's take a look at this. Now, remember that this is in pascals, right? So our highest load is, looks like on the back. No, it's on the bottom here, just because it's red. Everywhere else seems to have a nice even distribution, which shows our design is good. You know, if it's got a sudden spike like this, that's bad for the design, but in this case it kind of makes sense because the hole's right near the edge. I could simply move the hole up a little higher and it would be a little bit better, I would suppose. As far as the frame though, the frame looks pretty good. It looks, this part is getting there. Oh, actually, you know what? I just found the red part is in here. That's where the load is being applied. The problem is the fact that this part out here is also under a lot of stress. So we do have to watch out for this area. But again, for the rest of the frame, this part, this looks designed very well. You know, if it's sharing the load like this, the rest of it over here and here, it looks so blue that I think I can take away more material. But let's just take a look at, and go in here and look at the engineering data. And we can 2.9 times 10 to the 8. So it does indeed yield. 2.95 times 10 to the 8 is more than 2.5 times 10 to the 8. They're still pascals. Okay, so it does yield, but notice that, like I said, that is only right on the inside surface, right? Literally where it touches where the load is being applied. But it's only right where it's touching, right? The excess material around here is all green and yellow. You know, one solution would be to simply make the hole bigger. That gives us a little bit more surface area. Let's go ahead and do that. All right, so I've gone ahead and made this hole bigger, and I've also moved it up a little bit. So it's sort of like in the middle of where all this meat is, right? As opposed to being really close down to this bottom edge. And I already went ahead and ran the simulation. And guess what happens? Look at that. The highest load here is 1.66 times 10 to the 8, which you will notice is, if you go to engineering data, 2.5 times 10 to the 8. And if we take 2.5 divided by 1.66 and omit the times 10 to the 8 because they're both the same, that is factor safety of 1.51. Perfect. Also, what I found interesting was, if you watch this, right? Watch this animation. Right, you see how it's bending? Also, I understand that the front up here, oops, right, where it's where the front fork is attached is under a lot of stress. You see it's like, you know, high right here. But that's because it's a fixed constraint, and as it's bending, watch, see, because it's held still, right? So obviously right in this corner here is going to be a high amount of load. In reality, this would not be fixed like so. It would be able to rotate. So I technically need another like hole or something for the cylindrical constraint as opposed to a fixed. But for all intents and purposes, I think this is a pretty good result. And also what's interesting is check out this shape, right? Watch it move. Watch the motion of it, right? Tell me that doesn't look something like this. Doesn't it look really similar? It's pretty cool. Alright, so to recap in general what we've done today, right? We started out modeling something that was just basically, it kind of looked like a bike frame, you know, had the loads in the right places, had the fixed supports in the right places, but apart from that, the frame itself is just solid, literally solid, right? Then we put it into the topology optimization module where the computer will remove material, you know, based on stresses. From that, we get a very organic looking shape, which we can manually export, import it to here into another model, design around it as sort of like a guide or a template. We can run that through the FEA again, and check that the final result basically the frame that we designed that looks like this, it still passes. And then we check our factor of safety based on this number here. You get to choose, based on your judgment, I suppose, as an engineer, what you deem as an acceptable factor of safety. In this case, I don't know if the guy who's riding it is going to weigh 250 pounds or if he's going to be 100 pounds, you know. So I need to design in enough safety factor that this will survive, obviously, in the case where the larger person rides it, but also is acceptably lightweight for the smaller rider. 8% to retain, let's try, you know, if we put it at like 12%. Yeah, there you go. See what I mean? Like it's, you know, it will go to this extreme where it nearly removed our constraint. Start at 50%. If I leave it at 100%, it won't do anything at all. There we go. So yeah, at 99%, it converged on a solution and it didn't do anything other than chop the corner off. At some point, you get to decide which percentage on that slider is the optimal answer, and then go back and design it again and run it through the FEA and check your design. If it still passes, then you've successfully used topology optimization as a tool to help you as a designer to design something like a bicycle frame.